Off with our introductions. Okay. Hello, everyone. Thank you so much for coming. This is our final session of this symposium, this Fair February symposium. This week's theme is computation and democracy. This is our final session of this week. We have 3 young researchers who are going to be presenting short talks this afternoon. I want to thank everyone for all of the time that they've put into making this symposium a success. This includes Sohini Ramachandran, Alden Bumstead, Meg Lopez, Christina Mangini, and Shaharazad Haddad. So we're going to kick off with Suman Bera. If you have questions during the talk, feel free to unmute yourself and ask them. You can type them into the chat, and we'll also have time for questions at the end of the talk. And I will keep an eye on the chat if you're unable to unmute or something like that. So Suman Bera is a postdoctoral researcher at UC Santa Cruz. He works with Professor Seshadri there. He received his PhD in computer science from Dartmouth College under the supervision of Professor Amit Chakrabarti. Suman is mainly interested in foundational problems in data science. His recent work focused on large graph analysis, clustering, and fairness in algorithm design. An overarching theme of his research includes designing efficient and practical algorithms for various big data models while exploring the computational limits of such models. Before joining Dartmouth, he earned a master's degree in computer science from IIT Delhi in India and spent a couple of years working at Adobe India and IBM Research Labs. So with that, take it away.
Thanks, Mary. Thanks for the introduction. Yeah, let me share my screen. Can you see the screen? Is it fine? Okay. Thanks. My name is Suman Bera, and I'm a postdoc at UC Santa Cruz. And I'm going to talk about fair algorithms for clustering. This is a joint work with the partner of Chakrabarti, Nick Flores, and Mariam Negabani, and they are all at Dartmouth. And this work has been published at New Rips 2019. So let me start with the basic problem setup. So we are basically talking about a clustering problem. So we are given a bunch of data points, and for each data points, they belong to some protected groups. Now these protected groups can be based on ethnicity or gender. So for example, think of these protected groups as like male, female, or white, African-American, or Asian, things like that. And the goal is to cluster these points into goal is to cluster the points ensuring fair representation in each cluster. So for example, let's say this is an example set of data points, and there are 2 protected groups, red and blue, and we want to cluster them, let's say, into 2 clusters. So one possible solution is to create clusters like this, but then they don't have enough representation in each cluster from each of the protected groups. So we are not really looking at these kind of clusters, but we are more interested in clusters that looks like this, where there is enough representation from each of the groups. Now I'll make these notions more precise in the coming slides. So let me give some motivation behind the fairness model that we consider in this work. It's inspired by the notion of disparate impact doctrine. And in the clustering settings, it basically translates to the following. All protected groups in the dataset must have approximately proportionate representation in each cluster. So let's take an example. Let's say there is a protected group that consists of X% of the entire data. Let's say 20% of the entire data. Then there is this 80% rule of the disparate impact doctrine that kind of says that in each cluster, there has to be at least 80% of that fraction of that 20% representation for that particular protected group. So in this case, in each cluster, there has to be at least 16% representation of this protected group. So we model our fairness definition based on this. So formally speaking, for each protected group, we'll have 2 parameters, alpha I and beta I. And we have 2 set of fairness constraints. The first one is what we call restricted dominance. So this imposes restrictions against overrepresentation of any group in a cluster. So in particular, in each cluster, we want the data points from a specific group CI to be at most alpha I times the size of the cluster. So the fraction of points that are in a cluster from the group Ci should be at most alpha I. Now these alpha I and beta I parameters are user provided parameters. So these are input to our algorithm. So the second constraint is minority protection. So this constraint protects against underrepresentation of any group. So for a specific group Ci, we want this group to have at least beta I times the size of the cluster, many points in each cluster. So in other words, again, the fraction of points of this group in each cluster has to be at least beta I. So these are the fairness constraints that we consider. And let me give a summary of our results in this work. So we give a generalized and tunable notion of fairness in clustering compared to previous works. So we take alpha I and beta I for each of these protected groups as parameter to our algorithm. So it works with any such parameters. We give an algorithm that converts a vanilla clustering into a almost fair clustering. By vanilla clustering, I mean a clustering solution that does not explicitly consider any fairness notion in them. So we have a black box algorithm that takes such a solution and then converts into a almost fair clustering. Now it's almost because we'll see in the technical part that it does not achieve the fairness constraints exactly, but I mean, it's almost achieves them. And our algorithm works for a wide suite of clustering objectives, such as k-means clustering, k-median clustering, and k-center clustering, and so on. And one interesting feature of our algorithm is that it can handle overlapping groups, which was not present in previous works. So for example, each data point can belong to multiple protected groups, for example, African-American women. So this data point belongs to two protected groups. So it's a very natural setting, and our algorithm can handle this setting. So let me now give a little bit more formalism of the kind of clustering problems that we are looking at in this work. So we call this vanilla KP clustering problem. So in any clustering problem, we are given an input data set, and this input data set is embedded in some metric space. So basically there is a notion of distance defined over all pair of points. And also we are given an integer k, which is to say that how many clusters we want from this data set. This is unsupervised learning. So for example, let's say this is some bunch of data points that we are given in the metric space. There is a distance notion defined between any pair of points. And now the goal is to output two things. One is the set of cluster centers, which is at most k in size because we want to create k many cluster centers. So for example, these two could be the cluster centers that an algorithm produces, and also an assignment function, which basically maps every point to a cluster center. So it's basically which cluster a point belongs to, and while minimizing some kind of clustering objective. So the clustering objective that I have on the slide is a LP norm clustering objective. Well, that's not very important, but the basic idea is that I want to minimize some sort of clustering objective, and I want to output at most k many clusters. So the thing about this vanilla version is that the assignment function phi, this map, it's kind of redundant because every point will be mapped to its closest cluster center. So to represent a solution of a clustering, it's sufficient to just output these k many cluster centers. And for each point, it's going to be assigned to its closest center. So you don't need this phi function here. But we'll see why it's kind of important for the fair assignment problem. And that's just to have similarity. I have added it here. So some of the special cases for various values of P, when P is 2, this represents the classic k-means clustering problem. So for example, if we are really looking at the k-means clustering problem, then the clustering objective is to minimize the square distance of every point to its closest center to which it has been assigned to. So now let me define the fair k-means clustering problem, or more generally the fair version of this clustering problem. So as before, we are given this input data set and it's embedded in some matrix space. There is a notion of distance between the points. We want to create k-many clusters. And now we are given these overlapping protected groups defined on this data set. And for each of these groups, we are given these fairness parameters, alpha I and beta I. So let's take this previous example again. If you can see, there are three types of groups in this particular data set, and each of them are equally represented in the data set. So yeah. Now, the output for this fair clustering problem is again the same. We want to output k-many cluster centers. And also we want to output an assignment function which maps each point to one of these cluster centers. And it also minimizes the clustering objective that we have. And it also ensures that the fairness is satisfied in each of these clusters. So for example, this could be two potential cluster centers that an algorithm may decide to open or create. And then it has to have an assignment function that satisfies fairness constraints. So one potential assignment function might look like this. So this is to ensure that in each of these clusters, the representations are same. This is a strong constraint here, but it's just for an example. So as you can see, there are points in these clusters that are not assigned to its closest center, but that might be assigned to a further center in order to satisfy the fairness constraint. So that's why we need an assignment function for describing the solution of a fair clustering problem, whereas for a vanilla version of this clustering problem, we did not need such assignment function. And that's what makes this fair version of the clustering problem much harder. Okay, so in describing our results, we give a bicriteria approximation. So the bicriteria approximation basically means that in terms of the clustering objective or clustering cost, we are at most some row times away from the optimal solution. And we do not satisfy the fairness constraint exactly, but we incur some additive violation. So which means that, let's say I'm looking at a specific group CI and I'm looking at a specific cluster T. So the fairness constraint says that the values or the number of points from this protected group has to be between alpha I times the size of the cluster and at least beta I times the size of the cluster. But instead of that, we guarantee that it's plus minus lambda factor away, where lambda is a very small constant. So this is what we call rho lambda bicriteria approximation. Okay, so our main theorem is the following. We give an algorithm that takes a vanilla clustering algorithm, which has, let's say, a row approximation guarantee. And we give a rho plus 2, 4 delta plus 4 bicriteria approximation for the fair version of that problem, where delta denotes the maximum number of group a point can belong to. So delta in general is pretty small. So the violation that we incur, this 4 delta plus 4, this is quite small because delta's value is going to be quite small. And so I'll not go into the details of how we prove this theorem, but yeah, this is the main theoretical result of this work. These are some of the relevant work. This is a very fast evolving field. There are a lot of works that are coming out almost every month in this area. This is some of the other relevant works. So I'll give a high level algorithmic view of how we solve this problem. We'll not go into the details of various parts, but just try to describe the algorithmic approach that we have. So we call this a top-down approach. We first solve the vanilla version of the problem that does not look into fair constraints at all. So it just solves the vanilla version of the problem, and let's say it outputs some cluster centers, also an assignment function, which in this case is basically just assigning every point to its closest center. Now, once we have that, we fix this cluster center as the final cluster center, even for the fair version of the problem. So we just decide that we're not gonna change these cluster centers. And then we reassign the points, ensuring that these fairness constraints are satisfied while trying to minimize the clustering objective that we have. So let me take an example. Let's say, again, this is the setting that we have. We want to create 2 clusters. We have 3 protected groups. Each of these protected groups are equally represented in the data set. And we want equal representation in each of the clusters as well. So the first step would be to just run a k-means clustering algorithm on them, just a vanilla k-means clustering, which does not look at fair constraints at all. And let's say the vanilla k-means clustering creates these two clusters. Now, these two clusters are not fair according to our definition because not all groups are equally represented in each of these clusters. But what we do at this step is that we fix these centers, the cluster centers that the k-means clustering has produced, we fix them, excuse me. And then we set up a bipartite assignment problem. So on one side, we have these cluster centers, and on other side, we have these points that we want to now assign to these two cluster centers. And an edge weight is basically the distance between the point and the cluster center, the square distance, because that's the objective function in the k-means clustering thing. And then we try to solve this assignment problem, ensuring that it's fair. So basically, we reduce the search space of our problem to k-many cluster centers. So initially, the cluster centers were not decided when we are trying to solve the fair clustering problem, but by using this vanilla version of the clustering problem, we reduce the search space, we fix these cluster centers, and then we try to reassign the points while trying to minimize the objective function and ensuring the fairness constraints are satisfied. And then whatever this bipartite assignment problem outputs, we give it as our final solution. So the fair clustering will probably look something like this in this case. Okay, so the key step is to solve this fair assignment problem. And this is the major bottleneck for most of the fair clustering work that has come in the recent years. So I'll give again a high level idea of how we solve this problem. This is very generic, and we have not been able to find any way around that. So we basically write an integer program for this problem. We consider the linear program relaxation, the LP relaxation of this problem. We solve the LP, we get some fractional solution, and then we give some iterative rounding based technique to make it integral. And the nice thing about this rounding process is that the cost of this rounding stays optimal. So we don't lose much on the cost, but at this step, we incur this additive violation. And since most of the work is using this fair assignment problem as an intermediate step for fair clustering problem, most of these works also have this additive violation. And one interesting thing is that this problem, this assignment problem, we can easily show that it's NP hard. So we can't solve it exactly. So what we have given is exact in terms of the cost, but not exact in terms of the violation. So it's, in a sense, it's kind of the best one can hope for. So that's all I wanted to talk about the algorithmic results. I'll give some little bit of experimental results that we have. The first one is kind of the performance of a fair, of an unfair k-means clustering algorithm, off the shelf k-means clustering algorithm. The rate plot basically shows how much violation in terms of these fairness constraints are there in each cluster. So as you can see in each of these data sets, these are three different data sets. The k-means clustering algorithm can have quite a large unbalanced in the representation of its cluster. Whereas the blue curve is our algorithm, which basically suggests that we hardly have any violation. Although the theory says that we might have some violation, but in practice, we see that it's almost negligible. And the second interesting thing is that is a cost comparison. So here again, the red curve shows the cost of the k-means clustering solution, and the blue curve shows the cost of the fair clustering solution. We show that in order to achieve fairness, you don't actually compromise much on the cost. So even for various data set that we have considered, we have seen that in the worst case, the cost gets increased by maybe a factor of 15%. So it's basically suggests that in order to achieve fairness in clustering, you don't sacrifice much on the cost, whereas you can make your clusters much more balanced or much more representative of the entire data set. So I'll give some future interesting directions for the fair clustering literature. So one problem I already have mentioned, this fair assignment problem. So this problem is not really scalable because we are trying to solve a linear program to solve this problem. And so when the data set becomes really large and goes into, let's say, 100,000 or a few million data points, these linear program solvers, they start to take very, very long time. So designing a scalable algorithm for the fair assignment problem is a challenging task and is one of the most important problem of this area. Uh, Also, another interesting question is to understand whether one can design an algorithm that does not violate the fairness criteria at all, but maybe increases in the cost guarantee. And the third interesting direction is to consider a case where these protected attributes or the sensitive attributes are noisy. So in many data sets, these sensitive attributes are self-reported and they can contain noise. So for now, we are assuming that for each data point, we know exactly its level, whether it's a male or a female or what is the race. But if those attributes have noise, then can we still design fair clustering under those models? Okay, so I'll now conclude. So in this talk, we give a more generalized notion of fairness in clustering. We showed that our algorithm can take a row approximate vanilla clustering solution and produce a row plus 4 by criteria approximation for the fair clustering problem. We can handle overlapping group, and empirically, the cost of the fairness is quite small in all our experiments. So that's all I had. Thank you. And if you have any questions, please.
If I understood your work correctly, the lambda comes in as a consequence of approximating a solution to the ILP.
Right.
So I'm wondering, it seems like there's a computation accuracy trade-off there. Your final bound, you stated as what, 4 plus 4 delta.
Right.
I'm assuming that the approximation you give is polynomial time. So I'm wondering if you under some constraint on how much computation you're allowed to do, which would presumably depend on how good of a lambda guarantee you want, is there kind of a trade-off or a way you could more accurately solve that problem to reduce the value of lambda in the final solution?
No. So the thing is that the iterative rounding approach that we are using, we can show that it will lose this lambda, whose value is 4 delta plus 4 in the additive in the violation. So that the trade-off, or one possible trade-off, is that, so right now we are guaranteeing that the cost of the solution is optimal. So we are not losing anything on the cost, but we are incurring some violation. So one possibility is that if we allow the cost to go higher, maybe the solution that we are producing, its cost is twice as expensive as the original problem. Maybe there is a possibility that then we don't incur such a large violation. But again, so that, I mean, that part is not clear to us. We have spent quite some time trying to figure out if we can reduce or we can increase the cost, trying to reduce the fairness violation to 0. But we haven't been able to do that. But as presented, there is no trade-off in our algorithm. So the cost is optimal, and the violation, we have some tight examples where the violations will be 4 delta plus 4.
So if you were to solve the ILP exactly rather than use your iterative rounding, how would that affect the solution?
Then it will be an optimal cost. Then it will be an optimal solution. There won't be any violation. But the thing is that ILP solving takes much longer than the relaxed version. Yeah, but if you can solve the ILP exactly for small problems, yeah, we have done that. Yeah, then you get an exact solution without any violation.
Thank you.
I also have a question. So in your algorithmic approach, when you solve it for k-means or like the vanilla algorithm, and then you do these swappings, other work are also based on this, like they also like first find the unfair solution and then make some swaps, or they just start by optimizing a different function from the beginning?
No, all the other works are based on this. So once you have, so there were some initial work which took some different approach, but their fairness notion was much more brittle and only defined for 2 protected groups. But once it got generalized to arbitrary number of protected groups, this is the only approach that that's there right now. First, you solve the vanilla version to get these cluster centers, and then you solve this assignment problem. But like I should say that there are some scalable version of this algorithm which considers this core set version of this problem. But again, like once you construct a core set, which is a small representation of the entire data set, you still use the same approach to solve the problem for the core set. So we don't know of any other approach than these particular sets as of now.
Any other questions? All right. Well, thank you so much for such a great talk. We will move on to our next speaker. Our next speaker is Christina Mangini. She's a third-year PhD student at Sapienza University under the supervision of Professor Eris Anagastopoulos. Thank you very much. I did not prepare that name in advance. Thank you. So since August 2019, she's pursuing her research in the Big Data Group at Brown University, which is led by Professor Eli Opfall. After a life-changing year at EPFL as an exchange master student, she became passionate about Wikipedia. On it, she has built her work on detecting and mitigating structural bias on information networks. She thinks that Wikipedia is not only a beautiful place to learn something new, but it's also a source of inspiration to formulate interesting social science questions. Her work got the attention of Wikimedia Research, with whom she is currently collaborating to study the impact and usefulness of the hyperlink network beneath the encyclopedia. Recently, she approached the field of graph learning and learning with limited labels. In the past, she got a Master's of Science in Data Science, a Bachelor's of Science in Statistics, Economics, and Finance at Sapienza University. So again, during this talk, if you have questions, feel free to leave them in the chat or unmute yourself during the talk, and we'll also have some time afterwards. So go ahead, Christina.
Yeah, I'm sharing my screen. Can you see it?
Yep, looks good.
Okay, let me set the pointer. Okay, good. So thank you, Mari, for the introduction. And I'm really happy to be here presenting this project. So today I'm going to talk about auditing Wikipedia's hyperlinks network on polarizing topic. And this was a work, a joint work with my advisor, Eris Anagastopoulos and Eddie Upfall. So the goal of this work is to draw attention to and hopefully initiate a discussion about what's the importance of evaluating the Wikipedia's network of hyperlink to provide a neutral point of view presentation of topics that goes beyond the article's content. So Wikipedia is a web encyclopedia, so all of us know that nowadays counts around 1.1 billion visits per month, and this makes it the most visited website in the United States, followed by YouTube and Amazon. Other than recording this amazing amount of activities in terms of accesses, Wikipedia is also extremely alive, and in fact, it develops at a rate of over 1.9 edits per second. That's a lot. So it consists in many projects, and the biggest one is the English Wikipedia that includes more than 6.2 million of articles that increase every day, but by an average of almost 600 articles. So I think that this list of numbers is quite impressive, and at the same time, it's really kind of good proxy to understand the important role that Wikipedia nowadays plays in creating, shaping, and also broaden our knowledge. So I think in general that it's really worth to study Wikipedia. So knowledge on Wikipedia is distributed across articles. These articles generally describe concepts. They can describe specific entities like people, events, and places. And I don't know whether you ever try to write a Wikipedia articles, but sometimes it can get really frustrating and painful because before being published, an article needs to go through a revision process that generally not only verify the veracity of the information within the text of the article, but it also tries to put the formats of the article in standardized templates for specific subjects, such that users that are looking for specific information know exactly where they can go look to for finding what they are looking for. And another important thing to mention about the content of Wikipedia is that recently there were studies and people that started to observe that there were many articles, especially those related about controversial issues, that were embedding editors' bias. So Wikipedia took action from this and strengthened what is called the neutral point of view policies, which is an ensemble of principles that invites editors to be particularly careful about describing all the significant views that have been published by reliable sources, of course, on the topic they are describing on the article. So article interconnects via hyperlinks, and according to the Wikipedia's linking manual, so there is a manual for everything on Wikipedia, internal links can add cohesion and utility of the encyclopedia. And in particular, they allow the readers to deepen their understanding of a topic by conveniently accessing other articles. A consequence of the existence of hyperlinks within pages is that when as reader we access a page, we are directly exposed to its content, but at the same time, due to the presence of hyperlinks, we are indirectly exposed to the content of all the articles that are linked by the page we are reading. So far, from a content perspective, it has been a lot of focus on trying to have high quality pages. But on the other hand, if we talk about hyperlinks, even if there have been studies and algorithmic approach that help the editors in adding links within pages, those techniques generally consider the article similarities, and they don't really put attention in which is the way in which they are contextualizing the article within the network of articles on Wikipedia. So now that we know that Wikipedia is a set of articles and these articles are connected by hyperlinks, we can actually encode it as a directed network whose nodes are pages and edges are wiki links. And when we talk about wiki links, we refer about the links that connect articles in Wikipedia. So one main characteristic of this network is navigable, which means that the users that start from a page can sequentially click links continuing their session. So if we think about a broad topic that is distributed over multiple articles, we realize that the user's ability of navigating diverse aspects of a topic are really dependent on the existing connection among the articles in the encyclopedia. So a natural question that can raise is whether the current network topology actually guides the users in visiting pages presenting a broad and diverse aspects of users' topic of interest. Trying to answer in this question, taking into account the entire encyclopedia is challenging. So as a first step to study the phenomenon, we decided to narrow down the list of topics and analyze, and we decided to focus on polarizing topics, for which we believe actually to be particularly interested to understand whether the current network allows to visit diverse branches of the topic. So to this end, we introduced the idea of topic-induced network. So the topic-induced network are basically Wikipedia subgraph that are extracted from the entire Wikipedia's network. What is a topic-induced network and how we build it in particular? So suppose that we are interested in a topic that can be abortion, which is a broad topic that can polarize into articles about pro-choice and pro-life standings. So the first thing that we want to do is to be able to retrieve all these articles that are related to the pro-choice and the pro-life standing. To do that, what we do is to start looking for this kind of pages. So what to do is that we go to category that refer to these topics. And from this category, like in this case, we are looking for articles related to the pro-life standing. And so what we do is to go to the category anti-abortion, we take all the articles belonging to the category, and consequently, we also pick the articles belonging to its subcategories. So at this point, we have collected the set of pages that correspond to the pro-life standing. We can actually do the same and repeat the same operation for an analogous category that is referring to the opposite standing of the topic. And this is the abortion right movement. So from it, we extract the articles, and subsequently we extract the articles of the subcategories. So at this point, we have the other set of nodes of the other partition. What we do is that we can connect the articles belonging to the two partitions according to the hyperlinks among them. But since we are interested in understanding how the users are exposed to diverse information, not only given if they do one click, but also in sessions longer than one click, we are going to include in our network also a set of nodes that are not necessarily directed to the topic, but that are connected to it, to the pages composing the topic according to the current network topology. And then what we do is that we compress in a single super node all the rest of the articles of the encyclopedia. For the rest of the talk, I will only talk about the two partitions, but every analysis that we run, especially over a session of longer duration, will include all the nodes that are described here in the topic-induced network. So in particular, we decide to retrieve the topic-induced network related to some polarizing topic. As I was saying before, for instance, we consider the gun-induced network that separates in gun control and gun rights. We consider the topic of evolution that polarizes in creationism and evolutionary biology, and the other topics that are in the tables. So now let's suppose that we are considering one of these topic-induced network. And again, our aim here is to try to study the exposure to diversity of the users that navigate the network. So the first thing that we have to observe is that when users start their browsing session in a particular page of the network, that in this case we assume to belong to one of the two partitions we are interested in, what we observe is that at each page they can make a choice. So they can choose the next page to read. And generally, the amount of pages belonging to one of the two partitions to which they are exposed might be different. Like in this case, we have 8/9 chances of reaching a green nodes and 1/9 chance of reaching a yellow nodes. But then once the user decides to click and goes to the yellow one in this case, again, he's exposed to a different level of information with respect to the two partitions. In particular, this time there are more chances of continuing to read something related to the yellow partition instead of the green one. So we can see that quantifying the exposure to diversity becomes something that can be difficult to grasp by humans for two main reasons. The first one is that when we are given a list of hyperlinks in a page, for us, it's difficult to know a priori which are the partitions that these pages belong to. And so we cannot say we have 60% chance to move on the yellow one and 40 to move on the green one. And moreover, if we want to keep track of how the evolution of the exposure to diversity over a session of different length, taking the computation is going to be harder, and keeping track it's going to be harder. So we need to propose a metric that can try to measure this phenomenon. So in particular, this metric that we propose for each step of the navigation session tells us the probability of moving across and within set of pages. So let's suppose that we have, in this case, two sets. One is the green set and the other is the yellow set. What our metric computes is how likely is to reach the yellow partition starting the session from a green node. And in particular, we are able to compute the probability of reaching the yellow set for a given step L. So to do that, what we do is that at each step, we sum up the probability of ending up in a node J that belongs to the yellow set. And the way in which we compute these probabilities is through a variation of the page rank with restart that is defined in a Wikipedia tailored version. And I will not provide the details here about this project, but the general idea behind is that at each step of the chain, what we do is that we update the transition metrics of the process by taking into account the probability that at a previous step, an article could have been visited. And moreover, we also plugged into the model some click model behavior and some user navigation behavior. So since we have defined a metric to quantify the flows among and within partition, we now want to exploit them to study how much more or less likely is to keep reading of pages belonging to the same partition or reaching pages of the opposite side. So what we do is to first focus on what happened if we only consider the very local structure around the initial pages of the session. To this end, we consider a session of length 1. And in particular, we present a first example about the topic of evolution. Before proceeding explaining the example, just to give you an idea, what we consider to make these claims is that we take the previous metrics, that is quantifying the probability of moving of reaching at step L the green set by starting from a page in the yellow set, and we compare this probability with the probability of remaining at the same step in the partition of the initial page of the session. So if we consider the evolution induced network, what we see is that when a session starts in the evolutionary biology partition, the probability of visiting a page related to creationism is 83% less than the one of reading something about evolutionary biology. And we observe the same and even stronger tendency if the session starts in any creationism page. Indeed, the chances of exploring diverse information is in this case 96% lower than the chances of keeping reading pages in the same partition of the starting page. So, moreover, if we compare the probability of staying in knowledge bubble, where for knowledge bubble we mean the partition, sessions starting from creationism page have twice the chances of staying in the knowledge bubble than those sessions starting from evolutionary biology. So in general, about the topic of interest, about the topic that we analyze in this work, we summarize the following: that the local structure of the networks favors readers in exploring pages belonging to the same partition of the initial page session of the page more than those belonging to the opposite side partition. And on average, what we see is that the probability of reaching pages of diverse branch of the topic is 82% less probable than that of keeping reading the same partition articles. Then the chances of staying in the same knowledge bubble are unbalanced. Indeed, one partition locks the user within the bubble more than another. And last, an interesting thing that we notice here, and is going to be actually recurrent for our next analysis, is that when we embed in our models the user clickstream, the chances of staying within the partition double or triplicates. And this is a nice indicator that we will comment later. So at the same quantity we have just analyzed over the course of a longer navigation session. So in the plot on the right here, I present the plots for the topic abortion, but I will just comment the results overall the topic we analyzed. What we see is that for a short session that goes from 1 to 3 clicks, for both set of pages, we see that the chances of visiting the opposing set are lower than those within the knowledge bubble. Then we see that when the session length increases, users moving randomly have higher chances of getting away from the local neighborhood of the initial page. And so this situation implies that after many clicks, the probability of reaching any set of nodes, so any partition, correspond to the one of visiting the set of starting, the set starting from a random node in the network. So, and then for each network, we can identify actually a partition that is easier to reach from a random node in the graph. And we'll see later the direction of the current Wikipedia's network. And last, another interesting thing is that if we look at this blue line here, that represents users that move randomly, but actually at some point can come back to the initial page of the session, what we see is that their exposure to the other side with respect to the partition of the starting page, we see that it's closer and looks similar to the one that we observe in the session of clicks. So far what we have done is to compare chances of staying in knowledge bubble with those of moving to partition containing articles of diverse information. Now, what we want to see is the extent to which the network allows users to mutually move across the two partitions. So in this case, what we have is these two sets, and we use the metric defined before to know which is the magnitude of the flows going from one set to the other and vice versa. So given these metrics, what we do is that we are able to come up with those that we call the achieved mutuality, that is the reciprocated flow across partition, so the shared flow, and then we compare this quantity with the achievable mutuality, that is the maximum flow across the two partitions. This matrix that varies between 0 and 1, the chances that we have of moving from one side of the topic to the other, and tells us whether these are similar or not. So as a side note of this, it's interesting to notice that if we consider the non-reciprocated part of the flow going from one partition to the other, it would be nice, and maybe this can detect kind of the structural bias of the network, which actually favors the user to move from one side to the other rather than moving in the opposite way. So if we take a look at the mutual exposure to diversity, what we observe is that overall, our topics of interest show that the mutual exposure is always less than 1. That means that it's always easier to move across partitions starting the session from one of the two sides. And we also notice that the favor partition might change over the course of longer session. Then what we see is that click after click, the mutual exposure decreases. And so the structural bias of the network increases, meaning that it becomes much easier to reach one of the two partitions. And in the end, we observe that the local structural bias is smaller than the structural bias of the network. So of the structural bias that we observe in longer session. To conclude, if we consider the topic in the abortion-induced network, we observe that in the local neighborhood, the initial pages, on the local neighborhood of the initial pages, it's more difficult to move from pro-life to pro-choice pages than vice versa. And we see that this situation flips for longer session when reaching the pro-choice partition becomes easier. It happens the same for cannabis, where local is more difficult to exit from the prohibitionism knowledge bubble toward the activism one, and it's reversed when the length of the session increases. We observed similar circumstances for the other topic, and overall, we are able to observe that if we take a look at the local structure of conservative standing pages, what we see is that the structure of the network currently keeps them within the partition. Instead, if we look at the general topology that is reflected in longer session, it seems to be easier to reach pages related to liberal standing. So I want to conclude this talk stressing that the aim of the work was to draw basically attention and initiate again the discussion about the evaluation of the hyperlink structure of Wikipedia. And we believe that the observation we made can raise an interesting question for the Wikipedia community. For instance, starting from the fact that we saw that, especially within session of few steps, it's more likely to read about articles of the same standing. Something like this may sound really natural and reasonable, and it seems that it aligns actually with the current purposes of internal links that are made to connect concepts that are related to each other. But our question here is that how much is still this reasonable, and how much is it actually conform to the idea of natural point of view go beyond the content of a page. And moreover, similarly, we also observe that it's often more likely to reach an article in A starting from an article in B, and vice versa, and then vice versa. So we believe that some imbalances across the partition is reasonable, but the question that we ask is, in the moment this phenomenon keeps user locked in information bubble, how do we want to try to measure the phenomenon? So other than this philosophical question, let's say we can raise also more practical questions that are more related to the developmental tools that can help the editors to control the contextualization of articles within the networks. And also we can look forward the proposition of algorithms that try to change the structure of the graph such that the phenomenon of bias and diversity is controlled. Thank you for the attention. I'm sorry I went a bit long with the time.
So I have a question.
Sure.
You showed at the beginning this sort of overarching category. I don't know Wikipedia well enough. Is that something that people can easily find themselves, or is that like hidden?
Yes. No, yeah, actually, at the end of each Wikipedia article exists a section that is called categories, and typically each article of Wikipedia is categorized within a category. Now, we can have actually pretty interesting discussion about these categories because they are provided by editors. They are, of course, double checked, but there might be miscategorization, and there might be also the lack of categorization where it should be.
So do you think that these categories can be sort of a strategy for increasing, you know, connection between these sides? Like, is that a way to encourage like editors to get out of their own bubble and things like that?
I actually thought about it, but I think that it's more limited than a direct action on the network because it's less common that user access Wikipedia reading about a category page. So I guess that it's more likely that if I'm interested in a topic, I may go to the category page to see which article belongs to it. But I think it's kind of an unusual, I don't know actually, because I don't know, and there are not studies about it as far as I know. But I think it's less likely that users start their session and navigation of the graph from this category. So I think it would be not too much effective to act on the category, on this categories page directly.
I'd like to ask your metric of how often we stay in one bubble versus in another, I thought was very interesting. It seems to me like that has to be an inherently transient thing, because as we would go through this kind of random walk for longer and longer amounts of time, where we start would matter
I agree. Yeah.
So I'm curious, do you consider not only where we end up, but also where we would end up in an infinitely long walk in measuring this kind of bias?
No, we didn't do it because the idea was exactly for what you said, the fact that the more we go farther, the more we get away from the initial topics. And so the more we, in terms of mathematical terms, according to the model we use, the more we lose the dependency with the initial, the starting page. We didn't do the analysis on the long run because we thought that users generally have really short walks on Wikipedia. That's according to some studies. I guess that even consider a length session of 10, it's a lot. And so we were more focused on trying to understand what happened in the local structure of the network. And so in this case, even if the model was losing memories about what happened in the past, still it was okay.
So how do I know if we see that one page is well linked to the other and then the other page stays within itself a lot? How do we know that isn't just a consequence of there not being a lot of pages and links within one category, whereas the other one is very well connected?
We should go through the, we cannot know this information from the metric directly. Also the claim that we make are not made only on this metrics, but we also went inside the category and looked at how much they were connected inside and across each other and with the rest of the network. Sometimes it's another maybe topic, but this metrics has also a kind of issue related to the size of the bubbles. And so we try to mitigate it by sampling the nodes that we consider to estimate the probability of moving from one side to the other. But to know exactly what we saw actually is that sometimes that there are partitions that are smaller in terms of the number of articles that relate, like in this case, pro-abortion, pro-choice, for instance, it's a small number of pages, but they are so connected to the rest of the network that in the end, they, in the convergence state, let's see, when the path grows, what happens is that it's much easier to reach them rather than reaching the pro-life. Even if we look at the local structure, if we are in pro-life, we are much more locked in the bubble. That is a sign of the fact that likely they are more connected within each other.
Thank you.
Any other questions? Feel free to unmute or throw them in the comments.
I have a question. So what is the impact of the starting node, in the sense that are there starting node in one particular partition from which you are more likely to reach the other partition?
For the experiment we ran, okay, I didn't see it actually. Okay, for the experiment we ran, we have set the initial weights of probabilities uniformly for each of the nodes in the partition. So in the end, we kind of have the average of being in any of the node of the other partition. The model is built in such a way that you can, of course, specify the initial vector probability. And a nice way to do it, but it wasn't our first aim, is that you can actually weight the nodes according to the page views of the pages. These are numbers that are available. And another thing that I didn't mention in the talk is that anyway, the model that we built is based on different click models of users. So we both studied the possibility that the user just randomly click the links. And then we study the possibility that it clicks with higher probability links at the top of the page. And we also study what happens, what's the exposure to diversity when we directly embed the click stream of past users. And this is actually nice that we see that when we look at the click streams, the exposure to diversity to the other partition goes down. And this is an indicator of the fact it might be an indicator of two factors. The first one is that user, by their nature and driven by their information needs, just follow and continue to read pages that are related to the initial one. But at the same time, since we observed that especially on the first click, the structure of the network is pretty close to the knowledge bubble, what we ask, and another question that we raise is that is this a number of clicks that we register to similar page a consequence of the information needs of the user, or it is in some way related, and is it coming from the current structure of the network?
Okay.
I can't find the...
Okay, well, thank you so much, Christina.
Okay.
I think
I was able to sharing. Okay.
We'll move on to our final speaker of the day. So our final speaker is Dr. Shaharazad Haddad. She's a theoretical computer scientist who specializes in the Markov chain Monte Carlo method, social network algorithms, and measuring and mitigating polarity in networks. She received a PhD at Dartmouth College, focusing on combinatorics. After finishing her PhD, she studied big data and social network problems at the University of Rome, Max Planck Institute, and currently at Brown University. Shaharazad has been organizing a reading group called Algorithms for Social Good in the Data Science Initiative at Brown. And she also did tons and tons of work to organize this symposium. So we'll ask that you ask questions at the end of this talk. We'll have time then. And Shaharazad, it's all yours.
Do you see my screen now?
Yep, looks good.
Okay, thanks for the nice introduction, May. It would have been impossible without your help and other people's help, but now I start the talk. So I actually changed this talk a little bit from what has been advertised. So it's like a little bit more content than what I was planning to talk about. So I'm going to talk about polarization in web content and models and algorithms. This is a project that I worked on as a part of my work in the big data group, which is a group led by Professor Eli Uffa at the Department of Computer Science. It's a joint work with Christina Mangini, Matteo Ondato, and Eli Uffa. And some of this work has got accepted to be presented at Wisdom. Some of them is still under review. And some of the slides that I'm using now are what Christina made for our Wisdom presentation. So I thank her. Okay. Oops. So today I'm going to talk a lot about filter bubbles. First, I will motivate the talk by talking how the discussion of filter bubbles in the web started. And then I convince you that we need to have a different way of mathematically modeling filter bubble. Then I will present the mathematical modeling of the filter bubble. And then I will show you some algorithmic results that focus on mitigating bias on networks that come from recommender system or recommender systems or information networks. Okay, so right now we all know what a filter bubble is, but actually the discussion started around a decade ago by a lot of internet activists, the main one being Eli Pariser. So he wrote a book on filter bubble, which became the New York Times bestseller, and he also gave a lot of talks on TED Talks.
Mark Zuckerberg, a journalist, was asking him a question about the news feed. And the journalist was asking him, why is this so important? And Zuckerberg said, a squirrel dying in your front yard may be more relevant to your interests right now than people dying in Africa. And I want to talk about what a web based on that idea of relevance might look like. So when I was growing up in a really rural area in Maine, the internet meant something very different to me. It meant a connection to the world. It meant something that would connect us all together. And I was sure that it was going to be great for democracy and for.
So what Eli Pariser and other internet activists did actually was very important because it raised concern among computer scientists to fix this problem with the web. So a lot of researchers started thinking about how we can mathematically model filter bubbles and what are the solutions that we want to come up with. I have listed some of this work here, but you also saw some other works in the first session of this seminar today. Most of this work concentrates on the following modeling, which is in which the vertices of a graph are users and the edges show the relationship between these users. So for example, edges can represent friendships in Facebook, or if we talk about Twitter, it can be following or retweeting another person. So if you look at what sociologists or internet activists have framed the filter bubble, you will see that there are two different perspectives in which they formulate the problem. The first one is the existence of echo chambers, and the second one is the epistemic bubbles. So an echo chamber, what does an echo chamber mean? An echo chamber means that your friends magnify the importance of the content that is consistent with your prior belief. In other words, I have friends which agree with me, and even if there is content that is in disagreement with my prior belief, because my friends magnify what is in agreement with me, I just listen to them. The epistemic bubble is something else. Epistemic bubble says that the topics that are not aligned with your prior beliefs are far from your reach. And these two effects together define filter bubble as sociologists or internet activists have been talking about them. But unfortunately, most of the work that has been done in the computer science research just concentrates on modeling echo chambers, and there is little work to formulate epistemic bubbles. So now epistemic bubbles are very important because, as you just saw in the previous talk, there is a lot of polarity in Wikipedia, or in YouTube, there is evidence that recommendation graphs of YouTube can make users more radicalized when they navigate the recommendation system of YouTube. So we need to find a way to mathematically model filter bubbles, which actually models this epistemic bubble phenomenon. This is how we model the problem. We assume that the graph we are analyzing, the vertex set is the set of all the pages, and the hyperlinks and the edges represent the hyperlinks. Basically, there is an edge from one page to another if there's a hyperlink on that page connecting it to the other page. Now, since we are looking at a polarized topic, we assume that the vertices are either red or blue. Now, as I talked about before, we want to be able to also navigate, model the user behavior, and the users are navigating this network. So to this end, we use bounded random walks. So we assume that all the users there's some upper bound that we know, and this is an upper bound on the exploration session of users. And a bounded random walk is simply a random walk that takes 2 steps and then it stops. Now, using bounded random walks, I want to be able to quantify polarity of each page. So now, what do I mean by this polarity? Well, I want to be able to identify which pages or vertices are closely surrounded by the vertices of the opposite color and which vertices are not. And remember that our measure is bounded random walks. So if you want to remember one slide from this whole talk, it should be this one, in which we introduce the bubble radius, which is basically the expected time a bounded random walk takes to reach the opposite color. So in this example, the upper bound is 4, and we are looking at the expected value of the number of steps that we take to reach the opposite color. So this is, if you are familiar with random walk terminology, this is known as the hitting time. We are just adopting the definition of hitting time to bounded random walks. So now I want to tell you how we use this new notion of filter bubbles or bubble radius to analyze bias in information graphs and recommender systems. First, I want to tell you why these two applications are very different. Consider, for example, two different instances of them. For example, consider YouTube, which is a recommendation system, and Wikipedia, which is an information network. So recommender systems, since they are like more present in our everyday life, and since they have been a lot more criticized in the past decade, they already have come up with some diversity measures. What do I mean by that? If a recommender system, for example, let's say you are looking for a restaurant to eat in Providence, if a recommender system knows very well that you prefer Italian food to American food, it still shows you both Italian and American restaurants, maybe in a different order and with a different frequency, but it shows you both. Because recommender systems are already incorporating some measure of diversity in their algorithms. In fact, if you look at a book, like this book was written in 2015, you will find a chapter in it that is listing various measures of diversity for recommender systems. This is not the case for knowledge graphs. As Christina explained in her talk, study of polarization in knowledge graphs like Wikipedia is new. So if I look at this measure that I just defined, bubble radius, in two different networks, I will observe two different things. I will see that the bubble radius for recommender systems is lower than what you see in information networks. However, this does not mean that the recommender systems are already good. So if you look at, there is a still problem in recommender systems. For example, in March 2019, there was a terrorist who killed 51 worshippers in an attack in New Zealand. And it was when they interviewed him, it was known that he just became radicalized in his ideas by watching YouTube and other things on internet a lot. Which means that despite all of the effort that has been done, there's a still problem in recommender systems of YouTube or other things. The problem is that most of these recommender systems, they just try to diversify what they show you in the next step. And they don't consider the users who navigate their recommender graph, let's say. If there is somebody like this terrorist who just watches YouTube for hours and hours and keeps navigating this network, they can become exposed to polarity and become radicalized potentially. So now, having these two different applications in mind, we want to use our measure and define some measure of polarity. The first measure of polarity that we define is for recommender systems, and we basically want to see how diverse are the navigations in this network. For information networks, we are interested to find polarizing pages. Those pages that if you start exploring this information network in, there is a high probability that you will only be exposed to a one-sided view of the opinion. So for these two different applications, we introduced two different measures for quantifying polarity. For recommender systems, we introduced diverse navigability, which is basically the average of the bubble radius of the vertices of the same color. For information networks, we first define those pages that are polarized. We call them parochial pages. These are the pages which have a very high bubble radius. And then based on these parochial vertices, we define the structural bias of the whole network. Now I want to talk about some algorithms that we came up with. So again, when talking about algorithms, there is a very important difference between information networks and recommender systems. First of all, adding links to information networks is not costly. This is for two main reasons. Firstly, most of the information networks, for example, Wikipedia, are not extremely profit-based. Like the profit is not financial profit. I mean, extremely. Maybe they are, but I don't know. Secondly, it's like when you talk about information network, it's like a page that contains a lot of content in it. So just adding a hyperlink to the page does not cost you a lot. For example, one can read this page about Cairo Program of Action. This is about abortion rights. And they may think, if I just put a hyperlink on this particular place, it will make this page less polarized. And just hyperlinking this particular sentence does not have a lot of cost for the web administrator. This is not the case for recommender systems. Recommender systems are highly profit-based. They want to show you something that you potentially buy. So it is, and the second feature that they have is that the set of related items to an item is fixed. If you are trying to buy a shoe and the recommender systems is showing you a book, that's not relevant. So link insertion is not a very feasible strategy for recommender systems. So I first show you how we formulate this problem for information networks by inserting links to the graph. So the first problem that we consider is how to get rid of all of these parochial nodes. And we show that this is computationally hard even to approximate. So we reformulate this problem, and now we fix the number of edges that we want to add the network. This time we want to minimize the structural bias, and we come up with an algorithm which under some mild condition is an approximation algorithm. Now for increasing diversity in navigation, we want to come up with a less costly strategy than inserting links. What we do is we suggest swapping links. What does it mean? It means that if I am watching like this movie on Netflix, and Netflix is showing me this list of other movies, I have a higher probability of clicking on the top suggestion. And if this top suggestion has the same color or category as what I have just watched, then I will not have a diverse navigation in this network. However, by swapping these suggested movies, I will increase the probability of having a more diverse navigation. So based on this, we ask two other questions. If the number of swaps that I want to make is fixed, can I maximize diverse navigability? To this end, we design an algorithm, shuffling, and then we say that if each pair of swaps, if swapping each link has some cost, for example, let's say some financial loss in dollars or stuff, can we maximize diverse navigability within a budget? And then we design another algorithm. I'm not going to present a lot of details of how we design these algorithms. The only thing that I want to talk about is we need to design these algorithms, we need to define a new closeness centrality. So we talked about these centrality measures in the first session of this today's talks, and you saw that it's sometimes more beneficial for the administrators to modify some particular vertices in the graph, which has more influence on the total graph. So this is a notion of centrality. Now, because we are using this special definition of bounded random walks, we have to also modify the definition of centrality, and we define it as the average of closeness with respect to bounded random walks for a set. Now we prove that all of the algorithms that we have designed are constant approximations under some mild conditions. And we evaluate our algorithms experimentally. So the experiments that we have done is basically comparing our algorithm because we have just defined a new measure of polarity. It's a little bit hard to compare our work with previous work because basically they are maximizing a different objective function. But what we do here is we compare our algorithm with some simplified version of itself. And we also compare to some other algorithms, but remember that they are not maximizing our objective function. This is what we get for abortion on Wikipedia. And then this is the algorithm that we have designed for movies. It's for recommender systems. And again, we compare our algorithm to some variations of our own algorithm. So at the end, I want to end my talk with this conclusion. We always talk about what's wrong with the web, but it's also important to acknowledge that the web is useful. Especially social media, it gives voice to people whose voice is usually unheard. This is especially important for countries in which freedom of speech is at stake. So it is important that internet activists, sociologists, political scientists sit together and come up with a solution in which we make the web a better place. Thank you.
Questions?
I'm curious, can your method be extended to consider more than two groups, and how would that change parochial, what were they called, parochial nodes?
Parochial nodes. So in the information network analysis, we just consider two different groups because we are basically actually analyzing the two polarized ends of a topic, for example, pro-abortion, pro-life. Did I say it right? Pro-life, pro-choice. But for example, in what we did for recommender systems is, so you can have some categories. So basically we are looking at the hitting time of, let's say your category of moving is children, you look at the hitting time from children to any other category that is not children. But we haven't looked at like specifically how, I think it's interesting to generalize it to like specifically quantify how many colors you see in a bounded random walk. We haven't done that yet, but yeah, especially for the comments. Yeah.
I have a question. I think you kind of hinted at this at the end of that there's kind of two sides to this story. Like I do want the first link on Netflix to be the thing I'm most likely to be interested in. I think, you know, I don't necessarily want to go through and have that done for me. So that's not exactly a question, but I'm wondering what you think about that trade-off of kind of when do we want it to be that easy, and do we want these systems to help us stay where we're comfortable, and when do we want it to push us outside, I guess is my question.
Well, I think the reason that recommender systems are actually showing you what you want is that you do want what you want. That's why it's profitable. But maybe you shouldn't, I mean, it's maybe it's also useful like to have the option to see the other categories, like so I guess I don't have a very clear answer to that, but basically I guess the reason that this echo chamber or epistemic bubbles exist in the web is that because they exist in human societies also, they're just amplified in the web. So yeah, of course you want to see what you want to see, but maybe it's not the right thing to just show you what you want to see.
If I may follow up on that, in my work, one thing that I've found about recommender systems that is fairness related is that if we assume Netflix can show me more than one movie, presumably they're showing me a whole page, they don't necessarily want me to click on every single one of them. They'll get my money if they click on one or another. So they could fill the whole page with a bunch of crappy Hollywood sequels because I don't know, because my cousin watched one on my account. Or they could show me one. So if that's actually what I wanted, I could click it, but they could also show me a bunch of stuff that's more diverse. And I would argue that that is not only more fair in the sense of, well, I'm able to be exposed to more stuff. It's also more accurate in the sense that since they showed me a more diverse collection, there's more likely to be at least one thing I like, and all you need is one. So I wonder, Marie, to your question, like, is there actually a trade-off where you've claimed there is?
Are you asking me or Mary?
Well, both of you.
I think that to the question that you're asking is that, well, basically, if I want to get a little bit more technical, there are some movies that are related to this movie that you are watching. Netflix picks a top K of them and shows it to you. Your graph is bigger than what you see. So what they can decide is like, well, you are right that they can put some stuff there that you will never click on them. But if they are just showing you, like, for example, in Amazon and Netflix, well, so there is a difference in recommender systems. In YouTube, like, the recommendation goes down until the end of it. So you can scroll down and click on anything eventually. But in some of these networks, you don't see all of what is in the recommendation. So there are a few that are handpicked for you. So I guess those things, for example, in Netflix and Amazon that are handpicked for you, they're actually chosen carefully, also incorporating these diversity measures, but carefully to maximize profit. It's not like they just put you that thing there just to show diversity needs. It's that even that diversity thing is chosen carefully to maximize profit, because it's just like, 5 things are shown to you among many. Is that clear what I'm trying to say? But
it's definitely clear. I'm just wondering, are they necessarily at odds in this particular case?
At odds with what?
With is profit maximization at odds with showing something diverse and fair? No one quote me on that. This is a very specific case. I'm asking that question.
So maybe this answers your question. So this other strategy that we have for like swapping links, you would think that this is like very minimal intervention, but actually we saw that, this measure that we define can actually, like, with few swaps, to some extent, it improves the network. So define at odds. To some extent, it is at odds. To some extent, it's not. It can still be improved while we are maximizing profit.
Thank you.
I mean, it also seems like this is a place where the distinction between recommender systems and knowledge networks is important, because it seems like, like my first reaction is like, maybe it's not so important that I watch different kinds of TV shows on Netflix, but it's probably pretty important that I see both sides of an issue on Wikipedia.
Yeah, but strangely, it has not been studied that much.
Hello, can I ask a question?
Sure.
Actually, first of all, thank you for the nice talk. I just wonder if there is any constraint on your graph, because I don't see any. I mean, do you define some specific type of graph, or is it just a general graph?
Our graph is general for the information network. It just doesn't have absorbing states. Like if you think of a random walk on a network, well, it's not, there is no vertex that you would go there and you get stuck in there, basically. That's the only requirement that we have for our graph. For what we have designed, for what we have proved for recommender systems, our proofs also work if the graph is regular. So in case, for example, like if you consider the graph of Amazon or like any recommender system that always shows you k things, it still works.
All right, because I see that you have different colors of vertices. I just thought maybe, for example, if you can classify your graph as like a bipartite graph, for example, with two different colors, maybe you can use the property of bipartite graph and maybe do some mathematical, calculation on that using those sort of,
Our graphs are not bipartite. Because there is actually, if a graph is bipartite, the measure we are defining is very small. Like the definition of bubble radius is like the number of the hitting time of a bounded random walk to the opposite color. But if it is bipartite, the bubble radius is just 1, which is the minimum it can be.
I see.
So there is no, I mean, I guess the methods, we want these methods to be applicable, right? So there's
well, actually, I'm not expert, actually. Sorry for maybe, I mean, this question may look really silly, but I just know some graph theory, but I'm not really expert in the way I mean, the application that you use it in data science. That is what just came to my mind. Maybe you can use other properties of graph in your methodology. Yeah.
Yeah.
Anyway, thank you. It was very interesting. Thanks.
Yeah.
Any other questions? Shaharazad, do you want to say anything to conclude or either your talk or the symposium?
I'm supposed to give the closing remarks, so I made a slide for that. Okay, so I just want to thank everybody for taking the time and participating in our symposium. Special thanks to Christina and Marie, who helped hosting and organizing the whole symposium, and Sohini, who is the Data Science Initiative Director and helped with logistics. Eli Upfa and Cyrus Cousins, who are part of our group in Computer Science Department and helped a lot in organizing, inviting guests, and other things. Alden and Megan, the secretaries in the Data Science Initiative. Jesse, who helped us advertise our event in the CS, CS folks, and all the other speakers. So that's all for me. Yeah. Okay, so I guess that's the end of it. Thank you. Bye.
Thanks, everyone.